Hello everyone, and thank you for attending today's webinar, Measuring Aluminium Coatings with X-ray Fluorescence. Before we begin, I'd like to cover a few housekeeping items. At the bottom of your audience console are several application widgets you can use. If you have a question during the presentation, you can click on the Q&A widget and submit it. We try to answer questions during the webcast, but if a fuller answer is needed, or if we run out of time, you'll receive an answer later via email. A copy of today's slide deck and some links to additional materials are available in the resource list widget that looks like a green folder. You can expand your slide area by clicking on the maximize icon on the top right or by dragging the bottom right corner of the slide area. If you have any technical difficulty, please click on the help widget. It has a question mark icon and covers common technical issues. Finally, an on-demand version of the webcast will be available later today and can be accessed using the same audience link that was sent to you earlier. Now I'd like to introduce Dr. Bruce Scruggs, who is our presenter for today's webinar. Bruce is the XRF product manager at EDAX, and he has been involved with XRF for over 20 years. He holds an undergraduate degree in chemistry from Valparaiso University and graduate degrees in chemical engineering from the Massachusetts Institute of Technology. He started out working in applications for a company which builds innovative sample handling equipment for solid-state NMR. Bruce got involved in XRF when a headhunter confused RF radiation with X-ray radiation, and the rest is history. Now over to you, Bruce, for the presentation.
Thank you, Sue, for that introduction. Good day to everyone, and thank you for attending the last live webinar that EDAX will be doing this year. I'm going to be talking about measuring aluminum metal coatings on a few different substrates with X-ray fluorescence. And the idea for this webinar sort of came up when we were working with a customer who was having a problem in their vacuum deposition coater coating aluminum on silicon wafers. And so I wanted to sort of run through some of the different examples of that and in the process go through the customer's example as well. So our webinar is going to run about 45 minutes or so. We're going to focus basically on the capabilities of XRF to make thin film measurements in the lab and also in process control environments. I'll go through a bit of the theory behind the X-ray fluorescence. A little bit I'll touch on that, cover some of the instrumentation that EDAX sells for this kind of equipment, give you a little special explanation on calibration standards, and then run through some of the examples that I've done. Okay, so the simplest way and then the shortest way to describe what's going on in X-ray fluorescence, we have a model of an atom here. The X-ray fluorescence technique is measuring the elements themselves. We're not measuring molecules. We're not measuring bonding environments. We measure the element, and when we do thickness measurements, we measure the mass coverage. We measure the amount of element in the material. And we get a mass coverage out of that, and then you apply a density number to it to convert that into thickness. So what happens in our systems is we have an X-ray tube, we shine that onto the sample, the X-rays hit the atom, and if you have the right energy X-ray, you'll get an ejection of an electron out of an orbital. Here we have orbitals for K and L and M orbitals in the different colors. And as the atom relaxes back to ground state, you'll get fluoresced X-rays. These are the signal X-rays that we're measuring, and those energies are characteristics of particular atoms. Now, the one basic takeaway from this, I'll use some terminology later on, we'll refer to certain line series for the signal X-rays we look at. The K series, the L series, the M series. They come from, these different shells of electrons that we're looking at. And so we're looking at different energies of electrons. K is the highest energy, L is the next level of energy, and M is the lowest energy. And the various energies of X-ray signals that we look at can impact the range of measurement and the sensitivity of measurement we have for coating thickness. Okay, so the biggest advantage in using XRF spectrometry for analysis is it's non-contact, non-destructive. And we can also measure the samples as is. We don't have to do any sample prep on them, which makes it ideal for process control because you don't really want to do a lot of sample prep in that kind of environment. You can't. The technique can be adapted either to an air atmosphere or a vacuum atmosphere. And in general, we measure elements heavier than sodium. The sensitivity that we have to various elements depends on a lot of different factors. It depends on whether we're measuring in an air atmosphere or vacuum. It depends on how much the sample is loaded with a particular sample, a particular element, as to whether we can get good measurements on that or not. Depends on what size area we're allowed to measure. You know, if you're measuring a particularly small feature, then we may be more limited in sensitivity, or we may have to use other sorts of excitation methods, so it may affect the cost of the equipment. In general, the larger the area we can measure, the better the sensitivity that we have. And also, in general, the longer you can measure for, the better the sensitivity that we have. In general, our equipment uses an X-ray tube that's 50 watts in power, 50 kilovolts. This is about the power of a light bulb. So it's not actually very much power at all in these situations. And our detection systems are electrically cooled. There's no cryogens. There's no maintenance involved with the detector. So these are ideal components to be using in process control as well as in the laboratory. In XRF spectrometry, we can measure single and multiple layers. We can measure bulk materials. You can measure trace elements as well. In terms of the kind of quantification that we do in general for these kinds of applications, in particular coating thickness and whatnot, we employ computer modeling to model the physics of the situation that you have. This reduces the number of standards that are needed, and the examples that I'll show you today on using one type of standard or another in making a calibration over a whole range. What you do need to do in terms of coatings is you need to define which elements are in which layers, so that the computer model then can figure out the physics of the different layers. Sometimes the X-rays from one layer can go to excite the elements from another layer, and that's why it's important to know in what order and in what part of the stack the various elements are. Uses in process metrology. We talked a little bit about using a standard and what kind of accuracy you get in a model. One of the obvious uses is, of course, measuring drift from a target spec. And that's where you would want to have your highest accuracy is near the target spec. But it is possible, even when you're in, say, process startup, for example, and you're out of bounds of the calibration, you can still get useful information to just tell you you're out of bounds of the calibration. And you can get useful information about, okay, when I tune deposition parameters, am I moving closer to being inbounds or am I moving farther away? So uses there are you can measure drift, you can measure when you're out of bounds, and you can measure whether you're getting closer to the target or you're moving farther away from the target. The precision of measurements, the XRF measurements are governed by Gaussian statistics. Basically what that means is the more time that we measure for, the more X-ray counts that we collect, and the more counts that we have, the better the precision in our measurement. Our precision runs to the square root of the number of counts, the number of signal counts that we have. And signal counts, the precision, are affected by various factors like sample loading. The more sample you have, the more, should I say, more concentrated or the thicker the coating is, the more signal you'll have. The more excitation area you have, the more signal you'll have. Sometimes we can use different sorts of X-ray tubes to get a better efficiency for a specific example, for a specific measurement. And we take that into account when we're putting together a system for specific applications. The more measurement time that you have, the more X-ray counts you get and the better precision you have. So if you increase the measurement time by a factor of 4, the precision will improve by a factor of 2. General measurement times that we use in XRF, depending on what kind of precision you need, they typically run anywhere from a few seconds all the way up to a minute. That's your typical measuring time. We can set the systems up, of course, to measure for longer as well if we're trying to measure something particularly difficult to get good precision on, some sort of trace or very thin coating, for example. So this slide shows you a plot which outlines what a basic thickness measurement looks like and shows you what some of the basic limits are that you have. So on the x-axis, what we're looking at here is this is just a model now, looking at a single layer material on top of a substrate. And we're going to measure directly the X-rays coming off of the layer to determine the thickness of the layer or the composition of the layer. So on the x-axis, you have thickness. And in this example, we're running out to something like 40 microns. And on the y-axis, we're looking at the X-ray signal. And we're dividing that X-ray signal by the intensity that we would get from a layer that is infinitely thick with respect to X-ray. So you don't get any more response out of it if your layer gets thicker. So so basically we're normalizing to a value of 1 at that point. And what you see is that as the layer gets thicker and thicker, our signal ratio approaches a value of 1 because the layer basically becomes infinitely thick. When we're in a very thin regime, around, say, on this scale, a couple of microns, you'll see that the intensity, the signal ratio can change by, let's say, 20%, and you'll get a very small change in thickness. This is a relatively linear region of response, and this sort of determines the sensitivity for this particular measurement for very thin layers. And then you have sort of the nonlinear region in between, maybe up to about 80% signal, where you can go from, say, 20 to 80%, and you have a certain nonlinear response of the signal. It's in this area here where you typically need some sort of a standard to calibrate the models. Okay, so this table here is going to give us an idea of the kinds of range of coating thickness that we can measure for different elements and different kinds of X-ray lines. So if you look over on the left, we're running from titanium at the top down to heavier and heavier elements. And in general, as we go from the top to the bottom, it's set up so that we're looking at X-rays that are more energetic. On the right, then you have columns for the K-line X-rays, the L-line X-rays, the M-line X-rays. If you look at the K-line column, as we run down the column, the energy of the X-rays are getting higher and higher. And in this particular case, we can measure thicker layers because the energy of the X-rays is higher, and you have more penetrating power, more escape power, so your volume of interaction is greater. You'll see on this chart anyway, as we run to the K lines for platinum, gold, lead, these lines exist. It's just that they're very high energy. They're something on the order of 60 or 70 kV and higher, and we're running our systems at 50 kV. So we don't have enough exciting power for those. We use lower energy lines to measure those. So we'll have the L lines for platinum, gold, and lead to measure those thicknesses, as well as you have the M lines as well. Where we've marked on this chart, it's just by example. It doesn't mean that the series doesn't exist. It just means that we don't use it in the class of instrumentation that we are building. Now, the lower energy line series also have uses as well. You'll see, like for example, for the M lines, you measure up to a half micron or 1 micron and less. What these line series do give you is they're much more sensitive to thinner coatings. So the way that works is that instead of having this emission plot running from 0 to 40 microns, it runs from, let's say, 0 to 1 micron. And then you have 80% being, let's say, the useful region of the signal that you can use to make measurements. You have 80% of that range of XRF signal applying over 1 micron of thickness. So you have a lot better sensitivity to measuring thin coatings versus the same sort of signal that would apply over, let's say, 50 microns, where now your range of signal applies over a much thicker type of sample. When you get above somewhere the range of 80 to 90%, then small changes in signal near the asymptote result in large changes in thickness measurement, and it becomes more impractical in this region to make measurements. So there'll be some sort of a region cutoff at the max limitation for these types of measurements, and that's what we'll show in the examples. All right, so let's jump back into the presentation here. Okay, another form of making measurements, we can look at, instead of measuring directly the emission signal from the coating, we can measure the substrate signal and look at its intensity as a function of the coating on top of it. So now that substrate signal is going to be absorbed by the top layer. So this plot looks a little bit different. On the x-axis, we have the thickness range. On the y-axis, we have the signal intensity ratio again. But when the thickness is, when you have a very thin layer, then our intensity ratio is going to be near a value of 1 because we're measuring the substrate signal now. And as we get a thicker and thicker layer, our intensity ratio drops down to 0 because the top layer absorbs most or all of the substrate signal at that particular point. So you can you have sort of the inverse plot for this. Now, the physics for this kind of a situation here is a little bit different because these are some things that you don't necessarily have control of. It will depend on the energy of the substrate signal that you're looking at, and it'll depend on how absorptive the top layer is to the signal coming through from the lower layer. And I have an example of this to lay out some of the differences. You can also measure multiple layer stacks, and I show some examples of that. You can also measure the composition of the layers as well. So for example, in the electrical contacts market area, they use nickel coatings for certain applications and nickel phosphorus coatings for other types of applications. You can measure, for example, the composition of the nickel phosphorus layer. Another example of alloy layers in the photovoltaic market, you typically have some sort of a photovoltaic absorber layer. It's important to know what the composition of that is because it affects performance of the system, as well as you may have an electrical back contact. So the typical measurement would be to measure the thickness of the absorber layer as well as its composition, and then the thickness of the electrical back contact as well. And you can do this kind of thing with XRF also. All right, kind of instrumentation that we have. We have a process control unit on the right and a laboratory-based unit on the left. So we can use the laboratory-based unit to support the process control systems out on the floor. The benchtop system has a travel range of about 200 millimeters by 200 millimeters on the X and Y directions, and then the Z-axis travels about 6 inches or so. So you have a good bit of space inside the chamber. This is measuring in an air atmosphere. We use the same measuring head in this system as we use in the inline systems. And ideal uses here, you can of course use this for small scale quality control as well. You can use it for layer formulations and development of recipes on the inline system. You can test out ideas here and see, okay, can I make good measurements on the inline system with it, and then roll it out to the factory floor. The inline system, there's a couple different versions of this. I'm showing a floor version here that measures under ambient conditions. It's customizable. We can build it around your sample handling conveyance system. It has this particular system has a programmable XYZ stage, so you can make homogeneity measurements over larger pieces. You can measure across a panel. You can measure across a spool of flexible substrate. The size of these systems can be customized. We've built them relatively small, and we've built them to handle samples up to sample widths up to a couple of meters. So that's a bit of flexibility we have in whatever it is you're trying to measure. The kinds of systems we're showing here handle moving panels on a conveyor. We also can take the measuring head and build it into a vacuum deposition system. We can put a bucket into the vacuum deposition system. We'll have X-ray transparent windows in that bucket, put the measuring head in there, and we can make measurements through the X-ray transparent windows. Couple more comments about calibration. I started to talk about this in the beginning a little bit, and this is something that people generally tend to ask questions about. As I mentioned, when we're doing coatings, we need to define what elements are in which layers. And when you're doing coatings, you usually base this on some form of calibration. It can be very, very simple, or you can go all the way up to using type standards that are matched against the types of materials that you want to measure to improve the accuracy to the best level possible. What I wanted to do was comment a little bit about, well, what do I mean by standards? So there is an application note in the resource list that gives you a more detailed description and then some examples of what we've done in calibrating. But it can be something as simple as what I call using pseudo-standards. So they're not real standards at all in the sense that many people think of this, but it could just be pure infinite elements. So let's say that I want to measure a nickel coating. Well, I can calibrate measuring that by measuring a bulk, infinitely thick piece of nickel. So, maybe that nickel is 100 microns thick, and I measure that, and I tell the system, okay, this is a bulk material, 100% pure, and that'll give me a calibration coefficient for nickel. I can apply that calibration coefficient to all the elements, or I can make a calibration coefficient for each element in the recipe. It all depends on what kind of accuracy and what it is that we have available. And I'll show you an example later on where we calibrate for measuring thin layers just using a bare silicon wafer. Also, if certain compounds are not available as a pure element, for example, something like potassium, you can also calibrate using compounds as well. So we've done things where we've calibrated against potassium carbonate, for example, and we input the compound stoichiometry, and we get out a calibration coefficient for potassium. Now, we're not measuring directly the carbon and the oxygen in that situation. We know the stoichiometry, and so we put that into the model, and that will give us information about if you had so much potassium there and you knew it was in a certain stoichiometry, then you could say, all right, that's how much carbonate is there as well. Typically, accuracy in these sorts of methods is about 10% for 10% or better for thin single layers. You can also get type standards which are matched to your system. You can buy these commercially. If it's something proprietary, they're typically internally developed. EDEX is also available to work with customers and various vendors to have standards made as well. Accuracy in these types of situations depend on a number of factors, and I just wanted to touch on those. So the accuracy can depend on the standard deviation, the precision of the measurement. If you're making a single measurement, your error has something to do with the standard deviation based on that single measurement. Any bias in the model, typically as they get thicker, the model may be a bit biased, and it helps to have a standard in that area to remove the bias. And you'll also have error in the type standard itself. Typical errors in type standards run around 5% or so. If you need something better, that's the kind of thing you have to specify. The errors are combined as a sum of squares. It's the root of the sum of the squares of the errors. That's how they all sort of stack up with one another. And we can, work with you to minimize whatever particular error we're after. Your limits typically are in the type standards themselves. So it's a little difficult to move to get an accuracy better than what's in the type standard. Okay, some examples. This example having an aluminum coating on a nickel substrate. This I wanted to show you typically so you could see some of the different physics involved in making these measurements, either as an emission mode or in an absorption mode. So here we have a coating of aluminum on nickel, and aluminum is going to be the measured signal that we're measuring. And in this particular case, I calibrated it using a 4.8 micron aluminum foil on the nickel substrate. So it's a single type standard, single point type standard calibration. These are the results here. Now this plot, because now we're making measurements, and I didn't think to flip this around to match the earlier plots. We've got the signal intensity ratio on the x-axis, and we're getting the output aluminum thickness measurement in microns on the y-axis. So it's reversed from the beginning, and we're measuring the aluminum signal intensity in this case and calculating thickness. The reported values for the measurements are in the orange circles, and the measured results are in the blue diamonds. So what you see here in the first place, when you're looking on the far end, near where the results are going to asymptote near a value of 1, our measured results are coming out in the hundreds of microns. Our reported values are in the range of 25 microns to 250 microns. I specifically picked foils that were thicker so I could see where the maximum thickness range for these types of measurements are. So you can see kind of what happens there. Our reported, or should I say our measured results don't correlate with our input reported values. And that's because we're in a region where the layer is too thick at this particular point. So if I blow up now the scale on our thickness axis, now we're down at 30 microns. I have a range of foils that I measured that come from a company out in Long Island, New York, Calmetrics. So we have a 1/4 micron, 1 micron, 4.8, 13.5, and then I took two of these foils, the 4.8 and the 13 micron foil, and stacked them together to give me a total thickness of around 18 microns or so. So we can see roughly the thickness range that we can cover. So our maximum limit is somewhere around 18 to 20 microns on this plot. At 25, we're not getting good results anymore. In the 13 to 18 micron range, when we're doing a single point calibration at around 5 microns, our accuracy is in the range of about 10%. We could make that better by adding a calibration point out in the thicker end of the region. This is the kind of thing I would expect to see in this region. And as we blow we blow up the thickness axis on the Y, so now we're at a total range of 10 microns. You can see, the values that we're getting for the 1 micron value. The accuracy there is around 5%. The 1/4 micron is again around 5% in this particular case. And as you go sort of below the 1/4 micron, we're reaching a limitation in our precision in terms of getting meaningful results of measuring aluminum in an air atmosphere. So aluminum is a relatively low energy X-ray line, and as it goes from the sample to the detector through the air path, our signal gets scattered, and so we lose sensitivity. Our minimum thickness range is around 0.3, somewhere in a couple hundred nanometers type range. If you want to bump that up, we could go over to, let's say, a vacuum-based system where we pull vacuum on the sample and then we make the same kinds of measurements. And EDAX has higher-end instrumentation for that kind of measurement as well. Okay, now we're going to take the same samples that we measured in emission mode and we're going to measure them in absorption mode. And now I switched over to calibrating with a slightly thicker aluminum foil because our measurement range is going to increase. So here's the plot now in absorption mode. So now we're not measuring the aluminum signal directly, we're measuring the nickel signal coming through the aluminum substrate. And we've got our intensity ratio on the x-axis, our thickness calculation on the y-axis. Our range that we're plotting up there is up to 300 microns. Our orange circles are the reported values. Our blue diamonds are the measured values. And you can see we're getting pretty good results all the way up to, on this chart, to 140 microns. Here I've just stacked some reasonably thick aluminum foils together, measured their thickness with a micrometer, and use that as one of the points on the plot here. And so our high-end thickness range here is around 200 to 250 microns of aluminum, using the nickel as a gauge for how thick is the aluminum coating. This is because nickel is a higher signal energy and because the aluminum coating is not an effective absorber for nickel. So our high-end range in measuring aluminum coating thickness on the nickel is much higher than in emission mode. The physics for this situation are a little bit different. As we blow this up to look at where's our minimum thickness limit, what we can see is that we are getting results in the 10% range, around 5 microns or so, and below that we're getting some offsets where the measured values are coming out a lot higher than the actual foil thicknesses. And this is the reason for that is that as the coating decreases in thickness, and it's not very effective at absorbing the nickel signal, we don't have great precision in that range and looking at the nickel signal. It just looks like bulk nickel. So our minimum thickness limit is in the range of about 1 to 5 microns, somewhere in there. I didn't carefully try to plot that all out. The idea was just to be able to make some comparisons between an emission mode and an absorption mode. So you can see in this table here where the two ranges are dramatically different. The absorption mode, you can measure a much higher thickness level. The emission mode will give you access to thinner layers. Okay, now sort of the main reason for coming in and sort of the start of kind of the idea for behind this webinar was we had a customer who was trying to troubleshoot aluminum coatings on a silicon wafer. And they were having some problems with material that used to work well in their vacuum coater, and now they were having problems with it. So they're making relatively thin coatings on silicon wafers for the applications they were using them. The physics of this situation are a bit different. We're going to use the silicon absorption signal to measure the coating of aluminum because we want to go down fairly low, and you'll see the reason for this as we show the data. The silicon signal is about 5 times lower in energy than the nickel signal, and the silicon signal is just above the aluminum elemental absorption edge. So it means that silicon is very readily absorbed, the signal is very readily absorbed in the aluminum coating layer. So what this is going to amount to is that our maximum thickness cutoff for measuring in this configuration is going to be much lower than if we were looking at the nickel in comparison to nickel. And we should have a much better sensitivity for thin aluminum coatings because the silicon is much more responsive to the change in a thin aluminum coating. So let's look at this is the situation that we're measuring here. We've got aluminum on a silicon substrate. We're measuring the silicon signal coming through. And in this particular case, as I mentioned before, we're not calibrating against any coating thickness at all, any coating standard at all. I'm putting in a bare silicon wafer. I call that 0 microns of aluminum coating, and I make a measurement on that, and I get calibration coefficient off of that. And here's the results for this plot. So the signal ratio is on the x-axis. The thickness measurements are on the y-axis. And we're measuring the silicon signal intensity now. These two data points here, where we can look at our maximum thickness limit. So that's now on the left side of the plot. These are the 13.5 and 4.8 micron foils, and the results come out to 4 to 5 microns. So our limit for the maximum thickness range for this is somewhere in the range of, let's say, 3, 4 microns, something like that. And what happens in this region is basically the aluminum foil is so thick that it's absorbing most or all of the silicon signal. So it's a much different result than you get with a nickel absorption measurement, which is in the hundreds of microns. This is only a few microns. This is the value that we get off of a 1 micron standard. Our accuracy in this case, calibrating off of a bare silicon wafer, is about 5%. So that's pretty good for just putting in an infinite element and calibrating a 1 micron and getting a measured value for a 1 micron foil. Here's where the customer was making coatings. So the target was 200 nanometer coating on the silicon wafer. And the data points on the left within the highlighted area is material that has been made in the past. And you can see calibrating on the bare silicon wafer, it comes out, the accuracy in this case was pretty much dead on. We're getting reading back 200 nanometers for a 200 nanometer thick reported value. The value on the left is the material, the value on the right, the point on the right is the material that the customer is making now. And the first time I measured this, I said, okay, well, I'm coming out at something like 45 nanometers, and you're telling me it's supposed to be 200 nanometers. So, this of course triggered, all right, let's measure it again. And I got the same exact values in a repeat set of measurements. The customer goes, he's reviewing procedures and processes and all this kind of thing. He calls me back later and he tells me, okay, the coder isn't set up for 200 nanometers now, it's set up for 200 angstroms. So he's really putting down about 20, nanometers of material when he thought he was putting down 200 nanometers material. So that's the primary source of error there. We're still measuring around 45 nanometers when the coder is set at 20 nanometers. Now, the way these coders work, there's a monitor, coding monitor off to the side, a quartz crystal. The quartz crystal vibrates at a certain frequency, and as you deposit material onto the quartz crystal, the frequency decreases. So you can set these up and calibrate them for a certain set of deposition characteristics. But the monitor crystal is off to the side, whereas in the deposition zone, that's sort of in a different geometry in the system. And there's supposed to be sort of a tooling factor, a fudge factor between the monitor position and between where you are depositing material. So it could be that, where the coder is set up for, where we're getting 20 nanometers and measuring 45, there could be some miscalibration in this tooling factor. So that's another factor that the customer's going to look at as well. When we, to find sort of the minimum limit, our standard deviation is giving us, under these measuring conditions, we're measuring for about 1 minute in this particular case, is about 10 to 15 nanometers. So our standard deviation's in that range of noise level. So that'll give us roughly an idea of what the minimum is. I'm thinking our minimum is around 40 nanometers or so, about 3 times the standard deviation. But it depends on how much precision you need in the measurement as to maybe how long we have to measure for. So now we sort of summarize all the various measurements that we've made here. We've looked directly at the emission signal. The emission signal shouldn't really vary between whether you measure it on nickel or on silicon. It'll have some, there'll be some variation in that in terms of the minimum limit, but the maximum is going to be dictated by the energy of the aluminum. So that's not really going to change based on the substrate so much. You can see in the absorption measurements the differences between the minimum measurement range based on whether you're measuring on a high energy signal like nickel or on a low energy substrate like silicon. And then you can see the impact that it also has on the maximum levels. There's quite a bit of difference there in the range of what it is that we can measure depending on the setup that we're trying to measure. So just to summarize here, the advantages of using the XRF, it's non-contact, it's non-destructive, so that makes it ideal for process metrology as well as for lab measurements as well. We can measure layer thickness and composition. We showed an example here for measuring metals, but it's also ideal for measuring metal oxides, nitrides, carbides, anything where you've got something in the inorganic portion of the periodic table. We can measure single layers, multiple layers, and multiple layer stacks as well. EDX has a flexible product line. We have a benchtop system, an inline system, mat-line system, as well as I mentioned a system where we could put this into a vacuum deposition chamber as well. So our product is flexible in that we can customize the system to fit around the various conveyance systems that you have, the feed requirements, network control, that sort of thing. We can also operate at ambient or at higher temperature substrates as well. So with that, concludes the webinar itself. We'll take some questions here and see what kind of questions we have. So one of the questions we have, you mentioned measuring metal oxides, but the lowest element you measure is sodium. So how are metal oxide measurements made? Okay, this is a good question. So, for example, we've measured various kinds of oxide coatings: titanium oxide, zirconium oxide, these kinds of barrier coatings that are used in coating, say, packaging materials. What we assume there is the stoichiometry. So we actually measure the inorganic metal, the titanium, the zirconium, whatever it is, whatever the inorganic portion of that is, and we assume a stoichiometry between the titanium and the oxygen. So if it's titanium oxide, we might assume that's TiO2, and we measure the titanium signal. We input to the system, okay, this is what the stoichiometry is, and then that will give us the mass coverage and whatever density that the user has for that type of layer. We apply that as well, and that will give us the thickness of the metal oxides. The same idea applies to other more compounded type materials, metal nitrides, metal carbides, that sort of thing. Let's see. Yeah, can we measure along an axis in multiple locations? Yeah, so the question is, in these tools, do we measure just in a single position or in multiple locations? So these tools have the measuring head mounted on an XYZ gantry, and the systems where we talked about the inline systems, it's mounted on an XY gantry, so we can move over the whole piece. We can design a system that fits around the whole. Let's say it's a panel or it's a spooling flexible substrate. We can measure across the width of that component, or we can measure in multiple locations to look for homogeneity of the coating that's being put down over a larger area. You can do something similar in the vacuum deposition systems as well, but it's usually in the vacuum deposition systems you have some sort of a spooling flexible substrate. So we could measure across the width of the substrate, for example. Let's see. Okay. That was answered. Okay. Yeah, so the question is, we have a continuous web with a light metal coating. Can your system be adapted for this application where we look at zinc for the main part along with gold and silver at the edges? Yeah, that can be done. We can, as I said, we have a measuring head that can move across the width of a sample, and it's very good for measuring zinc, gold, and silver. These are all very good elements which will generate X-ray signals, which can be measured by XRF. Okay, let's see. All right. Okay. Okay, so another question, does this work for aluminum oxide coating on an iron substrate? Yeah, it would also work for that. In this case, what we would do is we would put in whatever the oxide stoichiometry is for this, and you can either measure the aluminum signal directly, and assuming a certain stoichiometry, you can get thickness that way. Or you can also, it's depending on the thickness of this, the thickness you're trying to measure, you can also measure the iron substrate signal as well. and you can measure a much thicker aluminum oxide coating. Okay, how sensitive is the system to small amounts of contamination or native oxide growth on a bare silicon wafer when using it for calibration, as in the case of the, yeah, okay. It's probably not very sensitive to the silicon oxide layer itself, on the native oxide that builds up on the silicon wafer, because the penetration depth of our measurements is going to be a few microns. Excuse me. So I suspect the native layers are, I'm not actually sure how thick the native layers are. They're probably on the order of a few nanometers or so. So the native layer oxide is going to be drowned out by the general volume of interaction for the silicon that we're measuring. There was another question here. Can you use XRF to measure the intermetallic layers that form between two metal layers? This is more difficult for XRF to measure. So if I understand this correctly, let's say you put down two metal layers, and you, in the process of doing that, you form some sort of very thin alloy region between the two layers. What happens in this case is we're getting signal from both of those metallic layers that we're measuring, and we're getting the value of mass coverage for each of those. And there's no unique signal associated with the intermetallic layer. So it's difficult to assign any signal to the intermetallic layer in that case. So that's a situation where it's more difficult for XRF to make a measurement. Let's see. How effective is the system in measuring potassium compounds and silicon and aluminum coating continuous process? So we have used the system in trials to measure the amount of potassium and the amount of silicon in these types of aluminum coatings on aluminum metal. What we use in those cases is we're able to measure the potassium and the silicon. Usually these things come in some sort of a compounded form. So we're able to sort of work that all out by knowing the stoichiometry of the potassium compounds, for example. And one last question, can you get accuracy better than 5%? It is possible to get accuracy better than 5%. You generally need a type standard for that, and your type standard should have accuracy better than 5% at that point. It's possible, if you know that the accuracy of the type standard is biased in one direction or another, if you add more than one type standard into the calibration, you can get the accuracy to exceed the 5%. But you kind of have to know what the bias in the type standard is. It's generally easier just to invest more time and effort into the type standard development to get the accuracy that the target accuracy that you need. So that pretty much wraps up the question session. Once again, I'd like to thank everyone for attending the webinar, and I hope everyone has a great end of the year, and we'll be back next year with the start of a new webinar series. Thank you once again, and goodbye.